Uh, so I think I will first say that, like, before I started working on these, I not really had worked on epidemiology. Um, so I will just tell you what was the motivation why I started working on it. So it was around March and April when all these crazy things was happening. It was very frustrating. I'm from India, and you can see the people I worked with. Lorenzo, who is my PhD student in Oxford, and he's from Italy. Susana is a colleague of mine in mathematics in Warwick, and she's from Portugal. And Dante is in mathematics in Nottingham, and he's from Chile. So you can see we are all from different countries. And then my wife is also from Finland. So what bothered me at that moment was that how all the different countries were implementing their lockdown policies, and everybody was doing different ways. And I was not really understanding what was the mathematics or how do they justify. There are high-level mathematical bodies doing it, but they're not really giving much clarification. So I just wanted to understand a bit what's going on in different countries, like funny things like that. I've noticed in Finland they opened the libraries first, whereas in England they opened the garden shops first. So for the justification, or is this just pure politics? I don't know. So we did some work, and we have now presently funded our work by UKRI. So let's go with the work. So what we wanted to do in this work, as I mentioned, that a pure curiosity to understand how lockdown is designed, and kind of start a discussion with people, with the mathematicians, so that we can convince them actually this is meaningful, and it actually can have some sense, such that it's just not put it to on us, and we need to just follow it. And so I will also try to keep the talk today kind of in a popular level, so that everybody who has not done a lot of math should understand it. So one of the main goal was thought was that to have a lockdown, essential criterions, I think it should be data driven and rigorous. And we should have a proof from the data why we are doing it. And secondly, is quantifiable. I mean, this is quite tricky to say. I mean, you want a lockdown, but has that lockdown been actually implemented? Can you measure it, how much lockdown has been implemented? And if it has not been, can we recalibrate our strategies? So how do we measure lockdown? So we wanted to devise something which you can actually measure in practice and then recalibrate whatever we are doing. So these are the two things was in our mind. Based on that, the work does three things. First is modeling of the epidemiological process. I will say that we are not doing anything fancy or too much fancy here. I looked into all the other people, the very famous scientists in epidemiology who are established scientists. They did their modeling, and we kind of picked up their model and tried to utilize that in our framework. So our model is pretty much the standard models people uses. And then we did uncertainty quantifications of this model. And based on all of these, we tried to see what kind of lockdown would a data-driven scientist or statistician would do. So based on that, I will start getting first explaining what is our model, or what is the epidemiological model we are looking into. So to give you intuition, I will first start with this figure, which tells you how many people has been hospitalized due to COVID in all sorts of NHS hospitals we know. And here I have a plot starting from 1st of March and until 1st of December. Here is the 1st of November, you can see, and it goes on. So as you all notice here, a couple of things. So this is your first wave peak. I mean, we all have seen this in BBC News and everywhere a lot of times. So it's the first wave. And then we have seen this is our second wave. And then we are noticing here a plateau, actually. So these are all these kind of features we have seen. And then we have seen here for a lot of times it went down. The number of hospitalization went down quite a lot. And this was this July, August, September period where there's very few people infected, and it came back up. So at that time, I did not had the evidence that what could it have done, but we kind of intuitively thought something actually may explain this behavior quite simply, and so we looked into that and we worked with that. But now we have evidence, and it actually tells us that it may explain these things quite easily. So what is that thing, and which can explain this pattern? And my point is that this whole thing may actually be explained by Google Mobility. So what is Google Mobility? It's basically mobility of your Android phone. So if you have an Android phone, Google knows where you go and what kind of location it does. Of course, you need to keep your location open, activated. So if you have it activated, they're tracking you, and they kind of collected that data. And it's not only for UK, they are collecting that data for all over the world. And in UK, they do it for each individual local authorities, which is in England and Wales, there are 348. So they give data for that. So that data actually looks like these, which is basically a time series. Over the days, it varies. So this one is for UK. For whole United Kingdom, they provided a data set like that. So I'm starting on the 1st of March, and until then, they just had averaged all the data they had beforehand, and then they said that was like kind of 1, and then from then they start this like measuring it and publishing the data. You can see that at around lockdown period, 17th of March, I think the government declared you need to be staying home, work from home, and also some measures. All these things, the mobility here goes down significantly and goes down to the lowest point. Here, this one is for residential. So if you are in home, then that's your mobility. And you can see from that day, your mobility, if you're in home, goes up significantly, goes down. And this is the second lockdown, and it again goes up. And then blue one is for work. And then green one is for transit stations, like big bus stations, railway stations, and things like that. And then it's other. And what does that other stands for? This is crucial, as because this we will see plays a significant role. So this is restaurants, this is groceries, and then this is also pubs, and then this is also shopping malls, etc. So you can see when you think about lockdown, closing down restaurants, groceries, pubs, shopping malls, that's basically the main thing which has been affecting. And if you look into this red curve, there is a funny similarity with the previous curve we have seen. So there is a sharp peak, and there is a bit of a plateau. If I overlay that curve, it would actually kind of matches this pattern. It actually goes like that, and there is some plateau here. So this is the hospitalization curve I'm putting. So you can see that all the effects, if you have this mobility that affects the epidemics in a delayed fashion, as because if you get infected, you need some time to be infected and being hospitalized, infection to be spread. So that's what is happening here. There was a lot of activity there, and then we saw there is a high peak in the hospitalization. And as because the lockdown happened, hospitalization fell down. These are all intuitive. I will show them all these things through math. And then as soon as you gone back to everything opening up, these others goes up, and then you see a peak, and then it plateaus, and you are having a plateau. So we thought that using this mobility in an epidemiological model may actually be quite meaningful to predict the epidemic spread well enough. Also, crucially, you can see this Google mobility thing can be measured, as because Google is publishing the data, so we can measure it. And if we propose that in future, your Google mobility has to be, let's say, 0.4, 0.5 to keep the epidemic spread under control, then we measure that it was not 0.4, 0.5, but our strategy only made it to 0.6, 0.7, so we need to recalibrate our strategy. So in a sense, this Google mobility is actually something we can measure our mobility, a lockdown through, and we can control. So we tried to use that in our model. We used that in conjunction with some other data called contact matrices. This was collected by another project done by BBC called Polymod project. So they had collected here I present pictures of matrices C. So what do they represent? So they represent at each location. So this is at home, this is at work, school, and the other locations I mentioned before. So what does it represent? So here at each entry means that age group 20 to 39, and here let's say age group 40 to 59. So these will be an entry. So how average daily number of contacts a person in age group I has with people in age group J. So these kind of contact matrices are very, very useful in epidemiological studies, as because you can see that you spread your epidemics, or like you spread your disease through meeting another person. Especially for coronavirus, it has to be meeting another person. So these contact matrices are very important. In different locations they are differing, and it's also, we know for COVID it was very much about the age groups. Some age groups are later, like 60 to 79, 80 plus, they were affected much more. So they were asked to be staying in the home more drastically than the younger population. So these contact matrices play a significant role, and we have these kind of contact matrices for whole UK at all these 4 locations. Now we use the Google Mobility to come up with a dynamic contact matrix, as because what we are doing here, we consider these each contact matrices here, and then we multiply with some sort of a alpha I, and this is a time series. Each of them is time series, as because you can see these alphas are collected by M star, which is our Google Mobility time series we showed you, multiplied by a parameter which is unknown. We will consider this as our alpha I. So this is our, in a sense, the mobility. So intuitively, you can see that you take a contact matrix at a location and you multiply by how much people is actually active there. If you have less people active there, of course, the number of contacts will go down. If you have a lot of people active there, number of contacts will go down and infection will spread there higher. So through these time series of Google Mobility, we can actually somehow come up with a dynamic contact matrix, which we will be using in our work. So I will also keep some of the parameters unknown, like this alpha 1 to 3. This is the first 3 age groups. These are mainly concerning the people less than 60. So this is a parameter which we need to infer. And then we got into a slight bit of hitch here. We noticed that Google Mobility data is not really reflective for people more than 60 years of age. It has a multiple reasons, that like the penetration of smartphone on the elderly population is very low. Also, elderly population are sometimes very conservative. They're not using their location app open. So it was not very reflective when we did the analysis we found. So we kind of took constant mobility for them when you are in age group 60 to 79 or more than 80. And also the government asked them to stay in home. So we considered there will be more conservative. So these are all these parameters, of course, we need to estimate when we come up with these dynamic contact matrices. Now, having a dynamic contact matrix, how does that affect epidemiological process? You probably have by now have seen how epidemics works in lots of websites, newspapers, everywhere people has been explaining. So this will sound similar to those things. So I will not go into much details, but I'll just tell you a bit of it. So I'm actually considering one of the most simpler type of epidemics model, which is a deterministic epidemiological model. You can take a stochastic process, you can consider epidemiological stochastic process models, but here I'll just consider an ODE model. Here you can see that this is the total number of people who are susceptible in age group I the age group. So these are the people who is completely healthy and fit. They have no disease, or they don't have COVID yet. And ISCJ is the total number of people who are infected in the group J, and NJ is the total number of people in that age group. So you have a proportion of people who are infected in that age group, and then CIJ is the contact matrix, you know. So that actually determines, so you can actually multiply with SI. You can see that, okay, I have 100 people who are susceptible, and out of that 20 people comes who are infected, then in a sense you multiply proportionality. But then of course this beta is an unknown parameter which tells you in which rate your infection spread and how easily it spreads. Some diseases do not spread easily, and some diseases spreads very easily. So that's a parameter epidemiologists are very much interested in. So that with these, we decrease the number of susceptible people we have, and we increase the number of exposed people we have, and these exposed people later become infected with a delay. And you can see here the contact matrix we are using, that's a dynamic contact matrix over time, and this actually reflects how the Google mobility helps to determine this epidemiological process. Of course, we need to learn beta here. This is another unknown parameter. So you can notice I'm gathering the parameters which are still unknown, and I need to learn. This is our full model. You can see this is the susceptible compartment I talked about. They become susceptible to exposed, and then exposed goes to infected, but these infected people who are going to be later needing a hospitalization. And there are other type of infected people who do not need hospitalization. They just recover after some time. And I'm assuming that if you need real care, then and only then you would probably die. If you are just staying home and you did not need hospitalization, you would probably recover. That's an assumption we make. And these people also goes to two kinds of clinical categories. One is the people who will finally end up dead, and the people who will recover and be healthy. So data-wise, there are a lot of different data the government publishes, and which we try to use on. Here, I'm using only two kinds of data. Here, the total, so you can see that IC1 plus IC2, if we add them, there will be the total number of people being treated for COVID in NHS hospitals each day. So that's the data set we have access from government. They publish every single day. And then the total number of people who have died from COVID every day. There are lags and errors and observational errors and things like that, but still this is a quite reasonable data. And also to notice, this data is published in an age-structured manner. So that's because they tell you people of different age groups have died in different conditions. So we will be using these two data sets, our parameters in our model, you'll see. But of course, there are a lot of other parameters hidden we need to learn, which I'm not explaining much detail. So this is parameters, the rate with which you become infected, and then the row parameter decides whether you become an ISC1 or ISC2. We need a hospitalization, and then from there you need a serious care. You'll be going towards death, a P rho dash, and then the 1 minus rho dash here. So all these parameters you are noticing here, they needed to be learned to use in a model which is realistic. Now, a lot of parameters, and I actually claim these parameters are country specific. When we feed this model on different data sets from different countries, we have seen the parameters being radically different for different countries. There are always deviations. And some of the parameters, both country and age specific, they are age dependent in different age groups, like probability of you needing hospitalization. We saw people in the older age group, which is also, we know from news that they need more hospitalization, but you get a concrete probability. And if you are in hospital, then what is the probability of you dying in different age groups? Those are the things we, of course, get here. But one of the things I have seen in most of the epidemiological papers I've seen, very few people actually try to tune these parameters for the data set. Most of the, quite a bit of papers just use some parameters was tuned earlier in Hawaii, in the Chinese province where the epidemic started, and there was some estimates they're just using to learn what sorts of prediction it should be. Most of the prediction based on parameters were learned in some other countries. So transferability was an issue, and we saw that the parameters are quite different for different countries. That's because the model we are taking is a very crude model, and it has a lot of assumptions. So you really need to fit your model to every specific country, otherwise it does not really work. So the question is that if this is my model, and this is a structure I told me, and theta is all the parameter, let's say, collected inside my model, and this is the observed data I get, the date, and people who are hospitalized in NHS hospitals, and you get all this data. How can I learn theta? So this is a tricky question. We need to answer that in terms of the parameters defining the model. Otherwise, we do not know. And of course, this model is a crude model. Nature or how the epidemic spreads are much more complicated. So our model is misspecified. It creates uncertainty. Of course, there are a lot of observational error in the data collected. So both of these misspecified model and observational errors causes uncertainty to the model prediction and in the model fitting and in things like that. So that's why we did not want to learn a single parameter value for theta hat, an estimate for theta hat, rather that we will look into a distribution of theta, which gives given the data we get of this model. So for that, we resort to the traditional Bayes theorem, which basically gives you the distribution of the parameter theta given your data. And this uses three things. One is this is traditionally known as likelihood, which tells you if I know the theta, what is in a sense likelihood of having that data. It has not other interpretations, but I will tell like that for everybody to understand. And this is prior, which is previously known information about the parameter value. And this is the evidence of the model is called marginal. Now, this is the formula comes from Bayes, but the problem here is this quantity, the like probability or uncertainty of the data given the theta is not easily known in this case, as because which is called likelihood. It's not as because the model is misspecified and also there is observational error. So we not assume that it's to be known here. And we try to learn the distribution probability of theta given x with our algorithms here. So how can we do that? For that, we use a technique which I work quite a bit on, is called approximate Bayesian computation. I will keep ABC at a level which makes it interpretable to everyone. So what does ABC do is that you have nature. Nature provides you a data, so which is this dot here, which is x0. And then you have this model, which you have seen before. I take a parameter theta, and it produces a data. So you feed the theta, and you simulate the model, you get a data. Now, these data can be close to my observed data or far away to my observed data. Now, for different values of theta, I generate here different data. Now, I only keep the data points which are, let's say, close to some epsilon neighborhood of my observed data. And I throw away all the red ones which are outside of that epsilon radius. And correspondingly, I only gather those parameters which give me those blue data points, and I throw away the parameters theta, which gives me the red points. And you can actually show, if you do this way, in a sense, these finally gathered parameters is approximately distributed as the posterior distribution of theta given that observed data. Now, for our epidemiological problem, we will just use Euclidean distance between the observed data and the data simulated from the model. One of the main difficulties of ABC, you can see that you need to take a theta and you simulate from the m theta, which is very expensive. So if you have a more complicated epidemiological model like ours, it becomes more and more expensive. So you need to definitely use high performance computing. You need to spread it over lots of computation, and then you can get some sort of ABC type of techniques working. Luckily, I have worked on these things before with high performance computing. We have a nice Python package called ABCPy. We have used it. Before getting into that, I will give you a slight more intuition how ABC works. So we are interested, if you were in a pure Bayesian inference setup, you can say that I'm interested about the probability of theta given my y-ups. We can write it as proportional of the likelihood and the prior, which you can also write as an integration where you simulate a theta from the prior, and then theta, using the theta, you simulate a y-sim. And then you check whether your y-sim and y-ops is exactly equals to 0. Then you integrate over all possible y-sim. That's your general Bayesian inference can be written like that. So as a procedure, it's a very expensive way to do it, but you can also do it, and you can actually show that this gives you the correct posterior distribution, simulate from prior, simulate from the model generating process, and then check whether observed and simulated data are exactly equal to same or not. But the thing is that if you want to check this, this is going to fail for most of the cases, because if you go for a complicated model, it never actually exactly matches. And it is going to be very, very expensive. So that's why we do ABC. Only thing we relax here, notice here, this equality, we relax this equality by thresholding. We consider that if it doesn't need to be equal to 0, but if it is less than epsilon, the radius we mentioned, then we accept. Of course, this causes an approximation to the posterior you get. So basically, you do exactly same as before, but you check whether that is less than epsilon or not. Given that, you generate an approximation to your distribution and you get it. So finally, what would you like? So you would like to accept or reject if it is less than epsilon or it is greater than epsilon. And you take your epsilon going to 0. So here I draw this crazy scientist who simulates text from nature and text from model, and then compares. He accepts or rejects, and with very advanced ABC algorithms, it takes epsilon going to 0. As because this is very expensive, we need advanced ABC algorithms. We will not get into detail, and high performance computing implementation of that you can easily get into ABC Pi, which we, when I was in Switzerland, was working with the Swiss supercomputing centers. We have a good, rather decent implementation of that. So we have ran these things on high supercomputers to learn these parameters. And in this case, we had almost 30 parameters to learn. And some examples of the posterior distributions we get. This may not be super meaningful to you, but you can see that we get for every single parameter, we get some sort of a distribution which tells us the uncertainty in our model and uncertainty we will get for our prediction. So how do they look like that? So I will show you one of the parameters which is fairly of interest, which is the probability of you needing hospitalization when you are infected. So you can see we are getting, at least for UK, this was actually done for England, not for UK, sorry. So you get really low probability if you are infected when you are 0 to 19, 20 to 39 age groups. But as you go up to your ladder of age groups, we kind of give you a probability estimate for you needing a hospitalization. This is a violin plot. You get where is the probability mass is concentrated. And if you are in hospital, what is the probability of you dying when you needing? And also that we see that's fairly high for people who are in 80 plus age groups. So these are also probabilities you can learn. But we are also interested in the prediction performance of our model. So here I illustrate how our uncertainty in prediction we get for UK. So there are two things which we used as a data for. One is the daily number of disease, total daily people who have died. So the red is the median posterior prediction we get from our model, and then the green one is the observed data, and the band here you see that's the uncertainty in our prediction we are showing, and in general it fits quite well for UK. And then IC is the total number of people in the hospitalized, and you can also see the median prediction fits quite well. And this was done until 1st of September, all this study. And we are noticing here it is going up, and we see the second wave coming to happen. That we also see, we calculate the R number, which you probably have heard everywhere in the news by now. See here, we see the first R number was very high when the first actual epidemic was spreading, 1.05, lockdown happened, R number went down. You can clearly see the R number going down. And around, this is end of August, you can see our number coming back, creeping back, and it's like around 1. And then in September, we were estimating that our number would go up more than 1 and go higher and higher. I did not want to show what happens to predict, as because that's controversial. That's the time when a government opened everything up. And of course, we were predicting if you open things like that, things may actually go bad. And we saw the second wave coming. So we also tried to do the same experiment for another country, which is France in this case. We took the data for France. We saw the daily number of deceased for France, we did a bit overestimation. So the model here also, we had to learn the parameters for France completely separately from UK, and we found a lot of parameters for France were significantly different from the UK parameters. And my thought is that the parameters will be differing for every country, and as because the model is quite crude. But we also learned the hospitalization that fits rather well, and this is the R number for France, how it varied, and all of these things depends on what kind of lockdown measures you are implementing through the Google Mobility and how it comes into play. Now, how do you design optimal lockdown based on all the things we have seen? So until now, we have this generic SERD type dynamics. So that's our model. We use the Google Mobility data and then the public health data. All this data we have put together, so model and all of this data. And also we have the technique called ABC. So here we have the ABC, and this is our model plus data. And all of this together gave us the model parameters and then the uncertainty quantification we have gotten done. So given the posterior distribution of the model parameters, we now want to define some sort of a loss function and want to say what sort of lockdown we should be having in the future. So we would do this cost function based on the posterior distribution of the model parameters we got. I will explain that soon. So we will do a posterior loss-based cost functional, and these would depend not only the number of hospitalization or number of people dying every day, but also taking care of the economic cost. So we will take both sanitary and economic cost in our modeling, and that will divide our posterior loss-based cost functional. And this becomes a global optimization problem, and we will optimize the cost function, and that would, in a sense, give us an optimal lockdown policy. What you will see, what does it tell us? Now, let's first define the cost function. So this is our cost function we are going to handle with, and it has two components here. The first bit is basically the sanitary cost, meaning that we want to minimize the total number of people dying and the total number of people being in hospital not exceeding the NHS capacity. So the first one is the delta DIT, is the daily increase in the number of deceased in the age group I, and we sum it over for all the age groups. And then this is a function which starts penalizing when it's like maximum of IC, the total number of people in hospital, minus H max, which is the maximum hospital beds in a sense in NHS. If you increase the number of beds, then this will also change. And that's another cost. So this basically the first bit consider the sanitary cost. And then in our model, we did not have a very involved modeling of the economic cost, which we are presently working on, but we tried to model here the economic cost in this manner that in different locations, if your mobility is 0, there basically you do not want to keep it to be 0, you want to bring it up to 1, your mobility in each of these locations, and for each of the locations you get penalized by some epsilon, so epsilon star for school, others, and work. And this epsilon, choice of epsilon, bases on the politicians, bases on the economists, how they want to control. Do you prioritize your schools to be open? Do you prioritize your works to be open? Or do you prioritize your restaurants, pubs, and other things to be open? So this there is a choice. In our paper, we look into different choices for epsilon, but altogether, we see there is a strong same recommendation in a sense we kind of get from all sorts of epsilon combinations, and I will show you that. Before, another thing to note here, we need an expectation here, and this expectation is coming from the posterior distribution we talked about. So we need the posterior distribution of data in future, given the data we have observed. So you can see that how many people will die in future every day, how many people will be infected every day in future. All these quantities comes from our epidemiological model. So they're basically data D, and they also depend on the Google Mobility M star. And of course, this depends on M star. So the first quantity depends on M star, second quantity depends on M star, and the first one is an expectation with respect to this posterior prediction we got. So we need to compute this expectation. And another thing we have here is the R number. So we want to see when we are optimizing over an horizon, which is TH, that at the end, our R number should be small. It should low down to go below 1. That's our goal. So our goal, sanitary cost should be low, economic cost should be low, and the R number should be low also at the end. So all of these three things brings our cost function. People can question whether this cost a meaningful thing. This was our first try, and we came up with these, and we are now working on with a better cost function to optimize it better. But we need to compute the expectation. So how do we do that? We sample parameter values from the posterior distribution. We got it from ABC. And then for each of those parameters, we solve the epidemiological model forward using each of these parameter values. And then you marginalize theta, then you get the integrated posterior distribution of the data. And then you can just do a Monte Carlo sum using the forward rounds of epidemiological model to compute the expectation of the cost functional with respect to that distribution. So this is more or less a computational numerical strategy we take to estimate our cost function, and we minimize that cost over all possible M we have. So that's the next thing. So we want to minimize this cost function over MT, which will be the Google mobility coming in future, which we have not observed yet. So mobility in school, mobility in work, mobility in other. And we want to find what should be the mobility optimally such that we can control the epidemic in future. You can see that actually would tell you what would be your lockdown strategy in future. And we want to optimize it for TH many times or days in future. So unfortunately, this optimization problem is highly non-convex, as because the dynamics is nonlinear and the reproduction rate is at the end is an eigenvalue of the parameter dependent matrix. So you can see why is it non-convex. And finally, this thing is non-differentiable. So we decided to make a heuristics. At this moment, we are using a generalized simulated annealing or 2-1 annealing to optimize the cost function and to come up with the optimal lockdown strategy. So next, I will show you what kind of optimal strategies we have come up with. And that's more or less coming to the end. So here, what do we do? We actually train the model on different times. So this is first on 11th of April. We trained the model and forecast what should be the optimal strategy. We can see that here, these are the values. We can see these value, and these was the value we observed for the Google mobility in the lowest value at the time of the lockdown. So until 26th of April, our model has been telling us to not change anything, keep everything locked down as it is. So the work is at 0.3, schools are at 0.4. Sorry, this is the others are at 0.4, and then the schools are at 0.1 for the emergency stuff, what we have seen. But when we do again in 26th of April, recalibration of our model and finding again the optimal lockdown, we start noticing that the model is telling us that you can actually start opening your schools a bit. So this actually starts recommending us the school opening. And as we go on the 11th of May, it tells us the schools can be opened quite a bit, almost like 60%, and it increases as we go along. So the model actually told us that schools could have been opened much earlier. And then it also started telling me at around sometime in mid-June that work actually can be opened. But significantly, notice this straight line here. So that straight line stands for the other, which is the restaurants, pubs, bars, and the groceries and shopping malls, which kept it at exactly same as the level of the lockdown, what we had, the minimum it could go to. And the model or optimal lockdown always proposed that it should be kept the minimum level, it should not be opened. So it was rather flexible towards work, further flexible to the school, but those other things should have been kept low. That's the model suggests. I do not know. I did not want to comment here. So these are the questions. Should we have followed these, or should we have done something better here? And correspondingly, the R values, which we had, if we had followed them, what would have been the R values we get from our model. And then we recalibrated it on the 31st of August when I think we kind of thought the 1st of September schools have opened, everything was open, pretty much everything went back to normal. But what did our model suggest that they did for England? It actually told us you can keep your work and school at fairly high level. We predicted it for the whole year until 31st of December. So work and school can be like at around 80–90% opening. But it noticeably, this is the other, which is the restaurant, bars, and school, all those grocery shopping malls. Of course, I understand there are a lot of other choices to be made, but what we just chosen, based on that, this keeps on the lockdown level to the lowest level. And the same thing we saw for France also, and the others were kept quite low. And we have seen if we just use the exact Google mobility, what we have actually observed, we could have predicted the second wave coming by opening the others so much drastically, what we are seeing at this moment. So that's more or less our work. We kind of come up with a loss function for the whole England, and we tried to find what should be the optimal lockdown in future, and we did some prediction. What we are presently doing, we are looking into the Google mobility, which is actually available for all the local authorities. So we probably can come up with a local optimal lockdown for each local authorities, which is 348 for England and Wales. But notice each local authorities are connected with other local authorities. That's because people live in one local authority and they commute to another. So we are also looking into the flow network of commuting, which get from the 2011 census data. So we have built a network model of epidemics based on and coupled with the Google mobility. We're working on it. And this is our website where you will find these new models soon. We'll publish there, and then the works and optimal lockdown strategies for each locations we should be doing. Hopefully, I strongly hope this is almost my conclusion of my talk, and I'm hoping that nobody would need to give any heed to my lockdown strategies for these COVID pandemic, as hoping this vaccines will be coming soon and everything will be good. And we are hoping for a good new year. But hopefully, if God forbid not, there is no another pandemic, but if it comes, maybe some sort of data-based, rigorous, optimal lockdown strategy would help us to convince people that this actually is something meaningful and we can trust on it. So saying that, I will conclude my talk. Thanks for your attention. And if you have any questions, please.
Thank you so much. That was fascinating and very thorough and in depth. So I really appreciated that. So we will start with the question that's just been added to the Q&A. So you said that Google mobility is affected due to the fact that people over the age of 60 are less likely to own a smartphone. This is going to skew the data. So the question is, how can this be fixed to make sure the data isn't skewed and therefore the model isn't incorrectly produced?
Yeah, so, I mean, I think like we have to, I mean, we did not look into very details, but like the penetration of the smartphone in different age groups can be utilized to correct the Google mobility for those. But the assumption we also made that it being constant over that age group was the reason that there was a strong government advice that if you are more than those age groups, you should be staying home. So that's why I thought it corrects the unavailability of the Google mobility data. And I'm pretty sure in a future couple of years, the penetration would be better in those cases. And we also have now the NHS app, which collects more data from people's being traveling and in the contact. So those probably can be also coupled with these things. And frankly speaking, there is data which we do not have access, which is not Google mobility, but the location of each phone, which every telephone service provider has. If they give us that, then we can use a much better mobility data and can be used in this model.
Yes, that's a good point. So you essentially, there is probably a skew, but the reasonable assumptions imply that it's probably favorable. The skew.
Yes, yeah, that's what I believe. Yeah.
There's a follow-up, which is how does what you've discussed relate to the tier system, and specifically how can it be used in each county to determine what tier each county should be in, and why?
That's our goal. Yeah, so that's our goal. I mean, what I mentioned at the end, that each local authority, LID, district councils, they can actually do the same analysis I have done. So we did this for the whole England, but you can, let's say you are the LID authority, you can do your own analysis for your data. Every local authority has their own data, and then you can come up with what should be your lockdown strategy for next, let's say, 2 weeks, 3 weeks. But one difficulty I see there is that England is kind of a island, so you can model England easily. But if you thinking about, let's say, Warwickshire and London nearby, so they are very connected. So there will be a lot of people coming and going. So you also need to control the flow between these different local authorities. So that's why we are looking into the network modeling. But I believe still each local authority can use some techniques like that and decide which tier there are. But I'm not getting into this. This is a bit political.
Okay.
Which tier you are? Yeah.
Could it be useful to split other into smaller, more specific subgroups?
I think so. So that's one could be done. Like, let's say we have this flow network data from 2011 census. You can do a network science analysis. Let's say you can come up with the clusters where people travel to each other. So you do not need to go to 348. You can go to, like, let's say 10 big clusters, 20 big clusters. And then those clusters you can say that, okay, these clusters do not interact too much. There's not too much flow between them. So then those clusters use their data and decide their tier 2 or tier 3 independently. I believe that should be doable.
And a follow-on question. University students moving around, especially at this current time, moving for Christmas, will have a massive impact on these models. Is that correct?
I believe so, but I mean, yeah.
Yeah, right.
Yes,
so I guess the model doesn't know about 2-week quarantining periods and things like that, right? It just knows how much people are moving.
Yes.
Yeah.
So, of course, our model did not take care of the quarantine strategy. It did not take care of another very crucial bit is the testing strategy. Like, if you can capture the people who are affected, you can remove them if you test aggressively. So we did not include that in our model. And of course, if the vaccination start, how does that include the strategy? So I will say there are actually epidemiological models. It can be easily, our model can be extended to incorporate those things. We just kept it simple and tried to come up with a first proof of concept. But if you include those strategies, then you can still do an optimal control based on those.